अभिषेक, अक्षता, आनंद, अंजुम, बसवराज गडकरी, बसवराज ऐनापुरे, भाग्यश्री,
Present, sir.
ओके, भक्ति, भारती,
Present, sir.
ओके, चेतन कुमार, दीपक, दिव्या, गणप्रत्न शिवाजी, ज्योति, किरण, लक्ष्मीकांत, मानतेश, मुळे प्रेम, नागेश, नंदीश,
Present, sir.
ओके, पूजा,
Present, sir.
ओके, प्रमोद कुमार, प्रवीण, प्रियंका, संध्या, संतोष पुजारी,
Present, sir.
ओके, संतोष सोनार,
Sir, Santosh Pujari, sir.
ओके, शाबाज,
Present, sir.
ओके, शफिया, श्रीधर, सृष्टि, सिद्धार्थ पर्णेकर, सिद्धार्थ पाटिल,
Present, sir.
ओके, सुप्रिया, वंदना, वसंत, वेदता, योगेश, महेश, बाळेश, तैक मोहम्मद, प्रवीण, अभिषेक, ऐश्वर्या, अमानुल्ला, बंडोडकर तनय मोहनदास, भावराव, शोधन, द्यावाणवर अनिल कुमार शेकप्पा, नंदकुमार, प्रमोद, रोहिणी, रोहित, शशिधर, श्रीधर, स्नेहल, वैष्णवी, साईश, कार्तिक. In yesterday's class, I was discussing about the programming of timer bar counters. Let us continue.
Sir.
Yes. ಹೇಳ್ರಿ
28 present, sir.
ಹಾಕೇನ್ರಿ ನಿಮ್ದು ಅಟೆಂಡೆನ್ಸ್ ಕೊಟ್ಟೇನ್ರಿ.
Okay.
I have given. Okay. You are able to see the screen? Are you able to see the screen?
Yes, sir.
Okay. Take this statement of the program. Generate a square wave with on time of 3 millisecond and off time of 10 millisecond on all pins of port 0. Assume crystal frequency of 22 megahertz. Generate a square wave with on time 3 milliseconds, off time 10 milliseconds on all the pins of port 0. Assume crystal frequency of 22 megahertz. Taken? Okay. I hope you have taken the statement, right? Did you take the statement of the program? Okay. So what they are asking, we have to generate a square wave. On time is 3 milliseconds, off time is 10 milliseconds on all the pins of port 0, assuming crystal frequency equal to 22 megahertz. Right? Now, before writing the program, we have to do certain calculation part. We have to do certain calculation part. Calculation is as for the off time or off time. frequency is given by what is the clock frequency formula? Crystal frequency divided by 12. That we have discussed in our previous classes. Crystal frequency by 12 gives the clock frequency. Here crystal frequency is 22 megahertz. It is 22 megahertz. This divided by 12. See how much it is? 22 megahertz by 12. It comes out to 1.833 megahertz. Just check your answers. 1.833 megahertz. Next, we have to find the time period. Right? The time period is given by T is equal to 1 divided by F. Time period of the clock frequency is given by 1 by F. That is 1 divided by 1.833 megahertz. 1 divided by 1.833 megahertz. This comes out to how much? Have you calculated? 1 divided by 1.833 megahertz. It is 0.546 microseconds. 0.546 microseconds. Microsecond. Okay. Once we have calculated the time period, then the number of clock cycles that are required for timer to count, that is given by the formula T on or T off divided by T. So T off is how much? For off time, how much they are given? 10 milliseconds of the square waveform. It is 10 millisecond. This divided by time period we have calculated 0.546 microseconds, right? So 10 millisecond divided by 0.546 microseconds. That gives the number of clock cycles required for timer to count. This comes out to how much? Just calculate. 18,315 cycles. 18,315 cycles, clock cycles. That means the starting value that we have to store, right? So that we get the delay of 10 milliseconds of time delay is given by the maximum value, that is FFFFH of the timer. FFFFH in hexadecimal is equal to 65,536 in decimal minus this clock cycles, minus this many number of clock cycles or counts, is 18,315. This is equal to 47,221. Okay. That means the starting value, this we have to convert it into hex. 47,221 in hex is how much? Just see. Keep your calc in hex mode and tell me how much you will get. 47,221 in hex is how much? This is in decimal, 47,221. Convert it into hex. This will be equal to how much? B875 H, hexadecimal. This is we calculated for on time. Similarly, we have to calculate the starting value for the on time. Okay. So for on time, the calculations are like this. That is on time divided by time period. On, just try to understand the calculations. Calculations are important before writing the program. T on is how much? On time of the square waveform is 3 milliseconds. 3 milliseconds. This divided by time period. Time period is 0.546 microseconds. 0.546 microseconds. Okay. This will be how much? This will be equal to 5494 clock cycles. 5494 clock cycles. Fine. That means what will be the starting value, students? The starting value is the maximum value of the count, that is FFFF, or in decimal it is 65,536 minus 5494, number of counts, 5494 counts. This gives the starting value from which the timer has to count, that is 60,042. or in hexadecimal this is equal to EA8AH. Okay, can convert and check 60,042 in decimal, that is equal to EA8AH. What it means? It means that if we load the starting value of EA8AH in TH and TL registers of the timer, then it will count EA8B, EA8C, EA8D like this up till FFFF. So how many counts it will make? It will make a count of 5,494. That's why we have to subtract the 65,536 maximum value minus the number of counts to get the starting value, that is 60,042 or EA8A in hex. Okay. Once we have calculated the starting value to be loaded into the timer registers, then we have to write the program. Write the program now with the starting values whatever we have calculated. So the program will be which mode we are studying now? We are studying timer in mode 1. Okay, timer in mode 1 we are studying. So we have to make use of the tmod register, move tmod comma hash gate c/t bar m1 m0. Gate c/t bar m1 m0 is the structure, 8-bit structure of the tmod register. In that we have to store 01, that is 00000001. Okay, that means upper 4 bits is for timer 1, lower 4 bits is for timer 0. We are using lower 4 bits, timer 0, 01, 0001. So gate is 0. Okay, software mode, c/t bar is 0, it is timer. Then 01 is for the, that is mode, it is operating in mode 1. Okay, that means we are using timer 0 in mode 1, timer 0 in mode 1, mode 1 is 16-bit timer, 16-bit timer. Okay, then next we have to load the starting value for the off time first and then on time, or on time first and then off time, anyone we can do that. Move TL0 comma starting value is how much? Let's look back at the calculation. Hash 075H 075H. You'll see here, sorry, then move H0 comma hash 0B8H 0B8H. Okay, 7B875. This is the starting value for the off time, B875. Correct. Higher timer high we are storing B8, upper 8 bits. Timer low we are storing lower 8 bits, that is 75. Next, so once we did this, then we have to generate the square waveform on all the pins of port 0. It is move P0 comma hash 00H 00H. Okay, then move absolute call delay. So once the delay is called, first we are making all the pins of port 00. Then once the delay is called, right, the delay subroutine we have to write. So this delay subroutine is written separately, starting from the memory location. In some memory location we can write this delay subroutine. Delay, how we are generating the delay? Using the timer. So first start the timer. We are using timer 0. To start the timer 0, which instruction we have to use? Set bit TR0. Then again JNB F0 comma again we have to monitor the overflow flag, right? In previous class I was discussing, previous two classes, how to start the timer. Once we start the timer, then we have to monitor the overflow flag, right? If overflow flag is 0, it will jump to here only again. Then if it is 1, it will come out of the loop. It will come out of the loop. So once it comes out of the loop, we have to clear the timer register, timer run control bit TR0 for next round of operation, and then we have to clear the timer overflow. We have to clear the timer overflow flag TF0 for the next round of operation. Then it's a delay program, so return. Then we have to end this. Okay. So return means where it will return. It will return to the next instruction after the call instruction. Absolute call delay, here it was called. Next instruction, what we have to write? We have to store the on and off. That is, this is for off time. It's B875. Look here. This is for off time. It is B875, the starting value. Right? For on time, what is the starting value? For on time, it is EA8AH. EA8AH. Okay. EA8AH is the starting value. That we have to store now. To store that again, move TL0, comma, what is starting value? EA8A. So that is 8AH, okay, hash 8AH. Then move H0, comma, hash, how much it is? 0 EAH or EA, 0 EAH. Then move, you have to toggle all the pins of port 0 to generate the square waveform. So move P0, comma, hash FFH. Okay, once we toggle, this is remaining low and we are calling the delay, so it will remain low for how much time? What is the off time? Yes, what is the off time? Off time is how much? How much off time they have given? Square waveform. Off time is 10 milliseconds. It will remain off for 10 milliseconds. That is a delay. Then again it will return. This is for giving the delay of 3 milliseconds on time delay. Then it will become high. Then it will call the delay. Again it will call the delay. Absolute call delay. It will remain high for 10 milliseconds. Okay, it will remain high for 10 milliseconds. Right. So this is how we are writing the program to generate the square waveform. If we want to repeat it, then we have to jump again to back SJMP back. We have to jump to back so that it has to repeat. Clear here? So this is how we are writing the program for generating the square waveform. Okay, for generating the square waveform on port 0, all the pins of port 0 using timer 0 in mode 1. Is this program clear here? Yes, Nandish, program is understood?
Yes, sir.
Okay. Let us move on to the second example. So before moving on to the second example, let us see the mode 2 programming in mode 2. If we want to program in mode 2, this is how the diagram looks like for the mode 2 programming. Timer in mode 2 programming. Okay, that is crystal frequency is divided by 12 to get the clock frequency. C/T bar is 0, it is for timer, so C/T bar is 0. Then we get the clock pulses here of 921 kilohertz, that is 11.0592 megahertz divided by 12. Then this is the timer run control bit, TR, to start the timer. When the clock pulse is high, when this TR is high, the AND gate output is high, right? When the AND gate output is high, the timer is triggered, the timer starts to count, right? The starting value of the timer is loaded from TH register into TL register, and from TL register, whatever starting value is there, it will start to count. Okay, it will start to count. Okay, it will count from that value. It will go on counting whatever the starting value that is loaded from TH into TL. From that value, it will start to count, and it goes up till 255. After 255, it will come back to 0. So it will reset to 00. So once it is reset, come back to 00. The starting value, whatever is there in TH, again it is copied into TL, and again it will count from that starting value to FF or 255. Right? When it overflows or when it rolls over from FF to 00, the overflow flag will be set. Okay, this I have explained while explaining the timer programming modes, timer modes. That is, it has 4 modes: mode 0, mode 1, mode 2, and mode 3. Mode 0 is 13-bit mode, mode 1 is 16-bit mode, mode 2 programming is 8-bit mode, it is called auto reload mode, and mode 3 programming, it is called as split timer mode. Okay. So the characteristics, what all I discussed just now, the same are the characteristics of the operations of mode 2. Is an 8-bit timer. It allows values only between 00 to FF, because 2 raised to 8 is 256. So we can store only the values from 00 to 255 or 00 to FF into the timer register TH. Once we load the TH value, it will make a copy of TH into TL. It will make a copy of TH into TL. Then we are starting the timer. Once we start the timer, it will start to count, right? Then it will monitor the overflow flag. Once there is a overflow condition from FF to 00, the overflow flag will be set. After the timer is started, it starts to count by incrementing the TL register until it reaches FF. When it rolls from FF to 00, the TF flag will be set, overflow flag will be set. When the TL register rolls from FF to 0 and TF is set to 1, TL is reloaded automatically. This concept you have to understand. When TL rolls from FF to 0, the timer overflow flag is set to 1. Okay. Then TL register is reloaded automatically with the original value that is there in the TH register. So it will make a copy of TH value into the TL value, into the TL register starting value, and again it will start to count. But this reloading, it is done automatically. Remember, this reloading of the starting value that has to be counted, that is loaded from TH into TL. It is done automatically. That is why this mode 2 programming is called as auto reload mode. Auto reload mode, because the starting value is reloaded by TH into TL automatically once the timer overflow flag is set. To repeat the process, we must clear timer overflow flag, and then it is not necessary to program for the programmer to reload the original value. The programmer need not reload the original value. Just now I explained to you the program where the starting value was reloaded, correct? But here we need not reload the original value. It will reload by itself. The programmer need not reload the original value. We need not write in the program such a way that to reload the original value. Okay, it will do by itself. Okay, what are the steps to program the timer in mode 2? The same thing again. Load the tmod value depending on which timer we are using and which mode we are using, whether we are using timer 0 or timer 1, and which mode we are using mode 2, right? Load the TH register with the starting count value, start the timer, monitor the overflow flag using the instruction JNB TFX comma target. Okay, so once it is raised, come out of the loop, TF goes high, clear the TF flag, then go back to step 4. It will go to step 4, that is, it will start to monitor the overflow flag. Okay, from 6th step, it will not go to 2nd step. In the mode 1 programming, what happened? From the 6th step, it went to 2nd step. That is, the starting value was loaded again and the timer was started. Then it was monitoring the overflow flag. But here in mode 2 programming, what will happen? From 6th step, it will go back to step 4. From sixth step, it will go back to step 4. It will monitor directly the overflow flag. It will not reload the starting value because it is done automatically. Okay, we are not doing that. The timer itself will take care of reloading the starting value. Okay, take this example. Assuming that xtal is equal to 11.0592 megahertz, find first one, frequency of the square wave generated on P1.0 in the following program, and B, the smallest frequency achievable in this program and the TH value to do that. Assume xtal is equal to 11.0592 megahertz. Find first one, frequency of the square wave generated on P1.0 in the following program, and B, smallest frequency achievable in the program and TH value to do that. Take down this example. Taken, students? Is it taken? Okay. I hope you have taken this statement. Yes. Okay. So what they are asking, crystal frequency is 11.0592 megahertz. Find frequency of square wave generated on P1.0. They are giving the program. You have to find the frequency of the square wave. Second part is smallest frequency that is possible in the program and the TH value that has to be loaded to achieve the smallest frequency. To obtain the smallest frequency, how much is the smallest frequency? That is the one thing. Another thing is, for obtaining that smallest frequency, what should be the TH value that we have to load, that we have to find. Okay. Take down this program quickly. Take down this program. Move pmod comma hash 20h. Move th1 comma hash 5 set bit tr1 back JNB jump if no bit tf1 comma back CPL P1.0 clear TF1 SJMP back. Small program. Note down this. Move tmod comma hash 20h. Move th1 comma hash 5. Set bit tr1 back JNB tf1 comma back CPL P1.0 complement P1.0 clear tf1 short jump back SJMP back. Hope you have taken down the program, students. Yes. Now let us do the calculation. Here it is the calculation we are supposed to do. What they are asking, first thing, let us just check what they are asking. Find frequency of the square wave generated on P1.0. First we have to find the frequency that is generated on P1.0. Okay. So if you want to find the frequency, okay, the starting value is given. The starting value that is loaded in timer register is 5. So what is the maximum value here for timer in mode 2? Can anybody tell me what is the maximum value? Maximum value is how much? Yes, Nandish, what is the maximum value? Nandish, Siddharth, how much? How much, Nandish? Siddharth,
2, sir.
Siddharth,
Yes, sir.
255,
2, sir.
255. Okay, maximum value that can be
Yes,
stored in
sir.
the timer is 255 FF. Right? 255. One clock pulse is required for overflow condition. That is to count from FF to 00. Total 256. Right? So 256 minus the starting value. That is 5 minus 5 starting value. Okay. This into what is the time period? How to calculate the time period? First, let us calculate the time period. So frequency that is given is how much? 11.0592 megahertz. Okay. So 11.0592 megahertz, megahertz, megahertz. That divided by 12. This comes out to around 921 kilohertz. Okay, 921 kilohertz, right? Approximately 921. Here it is there, 921 kilohertz. Okay, so 921 kilohertz. That is the frequency, and if we want the time period, t is equal to 1 by f, it is 1 divided by 921 kilohertz. 921 kilohertz. This comes out to 1.085 microseconds. 1.085 microseconds. Okay, 1.085 microseconds. Right? Now 256 is the maximum value minus starting value 5 into 1.085 microsecond. The time period is 1.085 microsecond for every count of the clock pulse. Correct? So that multiplied by the 256 minus 5. The final value is 256 minus starting value, that gives the count. So number of counts is 251. 256 minus 5. That one count, for one count it is taking 1.05 microseconds. Therefore for 251 count, how much it will take? Cross multiply. So this will be 251 into 1.05 microseconds. So this comes out to 272.33 microseconds. 72.33 microseconds. Okay, 272.33 microseconds. Now this 272.33 microsecond, it is only half portion of the duty cycle. Okay, half portion of the square wave. Right. If we want full portion of the square wave, what we have to do? Yes, please. If you want the full portion of the square wave, what we have to do? We have to multiply by 2. 2 into 272.33 microseconds. 2 into 272.33 microseconds. Okay. So this comes out to 544.67 microseconds. 544.67 microseconds. 544.67 microseconds. Okay, so this is the time delay. If we want the frequency of the square wave, what we have to do? F is equal to 1 divided by, okay, that is 1 divided by 544.67 microseconds. 1 divided by 544.67 microseconds. This will be equal to how much? Just check. This comes out to 1.8597 kilohertz. 1 divided by 544.61 microsecond. If you calculate, it comes out to 1.83597 kilohertz. Okay, this is the first part of the example. Okay, first part of the calculation. Next, the second part of the calculation, that is part B. Okay, so for part B, what they have asked? The smallest frequency. The smallest frequency. Okay, the smallest. If you want the smallest frequency, then what should be the delay? How much should be the delay? Delay should be maximum. Time period, if it is maximum, frequency will be minimum, or it is smallest, because f is equal to 1 by t. Correct? So to get the smallest frequency, the t should be large. It is largest. Okay, the time period should be largest. Okay, so if you want the time period largest, then what should be the starting value in th? Yes, anybody? What should be the starting value in th if you want the maximum delay? Maximum counts, if we have, then we'll get the maximum delay. So what should be the count in th? Priyanka?
Yes, sir.
What should be the maximum value in th? What should be the count in th if you want the maximum delay? If the count is maximum, then the delay will be maximum. So the starting value should be 0, 0. Okay, it starts from 0, 0 means to 255, 0, 0 till FF, 0, 0 to 255. The count will be maximum, correct? That many number of counts into 1.05 microseconds. So maximum count, maximum delay, right? Maximum delay, then minimum frequency. This is the logic. Okay, maximum delay, minimum frequency. So if we want the starting value in th should be 0, 0 to get the smallest frequency, right? Then what should be the time? What will be the time delay? Time delay is given by 56, because ff minus 0, 0. Ff minus this 0, 0 is 255 plus 1 clock pulse per overflow, that is from ff to 0, 0. 256. 256 into 1.085 microseconds. 256 into 1.085 microseconds. That will give us the total delay. Okay, total delay, but it is for only half the clock pulse, only for half the time period. If you want the total time period, then this should be multiplied by 2. On period or off period will be only this much. If you want the total period, then we have to multiply this by 2, this into 2. So this comes out to 555.52 microseconds. 550.52 microseconds. Okay, so what will be f then, students? What will be f? Frequency will be 1 divided by t, 1 divided by t. This will be equal to, if we divide reciprocal of 555.52 microseconds, so this comes out to how much? 1.8 kilohertz. 1.8 kilohertz. Okay, so this is how we are supposed to calculate here. Is this example understood, students? Yes, Priyanka? Siddharth?
Yes, sir. Understood, sir.
Understood. Okay. Nandish?
Yes, sir. Understood. Yes, sir.
Clear?
Understood, sir.
Concept is clear?
Yes, sir. Yes, sir.
Okay. In the next class, we'll take up some more programs on Mode 2 programming, and then we'll start with the 8051C language programming on timers and counters. That will start in the next class. Thank you.